Suppose you have a really large number, let's say 100 digits long, and you want to know whether it's prime or not. Now this might sound like the sort of problem that only a mathematician would be interested in, but it turns out to actually be very practical. The algorithms that secure our data depend on primes of this magnitude. So that makes being able to detect primes of this size extremely important. So the best way we know of doing that uses something called Fermat's little theorem. So Fermat's little theorem is a 17th century result about primes that says they have a very special property. Specifically, for every prime p and every integer a to the p minus a is divisible by p. So you could just check. You could take some random integer a. You could see, is a to the p minus a divisible by p? If it is, then maybe p is prime. But this doesn't exactly work. There's some numbers called Carmichael numbers that are not prime, but which have the same property. So we want to study these Carmichael numbers to understand what goes wrong, and hopefully to develop better primality tests in the future that are 100% reliable. So, as you can see here, this is a logarithmic plot of the locations of Carmichael numbers. They seem to get more common. And indeed, Alford, Granville, and Pomerantz proved that there are infinitely many. But they didn't show that these gaps eventually shrink to zero. And that was what I was able to do in my project. So basically, the idea of their proof is they use something called Fourier analysis, which is sort of about studying functions by decomposing them into waves. They used Fourier analysis on a finite group. And they were able to do this to show that a certain random product had a positive probability of being a Carmichael number. Now, I wanted to show that there were Carmichael numbers in a bounded interval, specifically between x and 2x. So I needed to add another component. So I did Fourier analysis on the finite group times a copy of the real line, which represented the logarithm of the numbers. So the only problem with this method was that I had to show that a certain conspiracy didn't take place. So imagine soldiers crossing a bridge. If they're all going at different speeds, there's no problem. But if they're moving in lockstep, and that's the same as the resonant frequency of the bridge, it could collapse. So in this analogy, the soldiers are primes and the bridge is my argument. So I need to show that the primes don't have the same frequency, whatever that means. So this is a very common theme in analytic number theory, showing that there's no secret conspiracy among primes. And the famous Riemann hypothesis, which is an unsolved problem, asserts a statement like that. So there's been a lot of work on the Riemann hypothesis, and one of the things that's come out of it was the recent breakthrough by Zhang and then Maynard and Tao on the twin prime conjecture. So they proved that there are infinitely many pairs of primes a bounded distance apart. This is what you would expect if primes were sort of distributed without a bias, but it's very hard to prove. So using the same sort of technology that rules out conspiracies, I was able to show that the primes don't have all the same frequency, and that made my argument work. So I was able to prove that for sufficiently large x, there's always a Carmichael number between x and 2x. Thank you.